Today we're going to learn about binomial probability. So the word bi means two here, like a bicycle. So binomial distribution in one in which there are only two possible outcomes. So you might think of like flipping a coin. Like when you flip a coin, there are heads and tails. So there are two possible outcomes. I'd really like you to think about those two outcomes as success and failure, because we can kind of use these two things a little bit looser here in this case. So a die is tossed three times, what is probably getting exactly 1, 4. So at first, this might not look like binomial probability because aren't there six outcomes when you toss a die? You could roll a 1, 2, 3, 4, 5, or 6. But if you think about success and failure, so success is we want to get exactly 1, 4. So fours are success, right? Um, so 4 is considered a success. So um, like getting a 4 on the first roll. So these are three different events here. So I want to get a 4 on the first roll. I want to get a 4 on the second roll and a 4 on the next roll. And they're all independent events. So we're going to multiply here. The first one doesn't have any effect on the next one. And they're all the same, so it's easy just to multiply here. That'd be the easiest way. So you get exactly, oh, wait. Ooh, wait a second. No, I don't want to get, so the first one's going to be, we're going to say that's a 4 and that's not a 4 and this one's not a 4. So this does change. So I want to have success in the first one, let's say, and so that's going to be, um, in this case, 1 out of 6 times, that's going to be a 4. 5 out of 6 times, it's not going to be a 4. And 5 out of 6 times, it's not going to be a 4. So get your calculator out. We're going to multiply this. So this would be 1/6 times 5/6 times 5/6. And we get 25 over 216. Okay, so we get 25 over 216, whatever decimal that is. Okay, so, but I don't think we actually answered the question. We're coming close here, but it's really not quite accurate here. So the problem is we actually answered the question, what's the probability of getting a 4 on the first toss and then not a 4 on the next two tosses? But actually just said, I want to get exactly 1, 4. So let's think about the other possibilities. Well, maybe the 4 you want is in the middle. So say when I get a 4 in my second roll, I want to get not a 4 here and not a 4 here. So this would be 5/6. Well, this looks familiar, times 1/6 times 5/6. So you multiply those out, I guess you get 25 over 216. Well, we still haven't answered the question. We've figured out on the first roll, getting a 4 is that probability. In the second roll, getting a 4 is that probability. But what about the third case? So let's figure that out here. So this would be not a 4 here, not a 4 here, and a 4 here. So that would be 5/6 times 5/6 times 1/6, which is 25 over 216. So if you add those up, you're going to add those to get 75 over 216. That's the probability. That might simplify, by the way. Let's just look at that. 75 divided by 216, 25 over 72. So that would be 25 over 72. 20. So that's the probability of getting exactly 1, 4. Well, that'd be a lot of work to figure that out, especially if there's more than 3 different cases, which we could definitely see in some of your homework problems tonight. So there must be kind of an easy way to figure this out rather than having to redo the same calculation 3, 4, 5 times. So let's look at, oh, by the way, here's a little joke for you. This might be the highlight of your day. Did you really just use the binomial distribution for a problem with three outcomes? That would be so silly. Binomial, we're talking about two outcomes. That would be just ridiculous. So there's a meme, a math meme. I don't know if you've seen a math meme before, but they bring a little joy to your life. So I hope that one does. Because there's only two possibilities with binomial. So remember that with binomial, only two possibilities. In fact, we call success P, and we call failure Q. So Q represents failure and P represents success. That makes a lot of sense, but that's what we do. Probability of getting R successes and independent trials is this formula. So we have this NCR, you've seen that before this week, P to the R, Q to the N minus R. So what I recommend is let's do the same problem and just define our variables here. So P, so again, P was probably a success. So success is defined in this case of getting a 4. So probability of success is 1/6. Q is probability of failure, that's 5/6. N is like the total number of outcomes, and R is the number. It says N independent trials, R successes. So I want to get exactly one success. So I want R to be 1. But I'm really tossing this thing 3 times. There are 3 trials, so N is 3. So at this point, all it is plugging into this formula here, right? So we have all our variables defined. So this should be NCR, so this would be 3 choose 1 times P, which is 1/6 to the R, which is 1, times Q, which is 5/6 to the N minus R, which is N minus R is 3 minus 1, which is 2. So if you look at what this is, like, do you see how we're doing 5/6 to the second power and 1/6? We're multiplying. That's this part of the formula, 1/6 times 1, 5/6 to the second power there. And so we had to do this thing, in this case, if you remember, we had to do it 3 times. There were 3 times. We had to multiply, essentially 25/16 times 3 is 25/72. So if you do 3 choose 1 in your calculator, you'll probably see this. So 3 choose 1, so NCR 3 comma 1, we get 3, right? So this number represents 3 in the problem, which is how many times we had to reiterate it or do it over and over again. And so this ends up being, you end up typing in your calculator and you get, I'm not going to type it in because we already did, 25/72 is the answer here. So if you type that in, you'll get 25/72. I don't care if it's decimal or fraction, doesn't matter to me. Okay, so let's try this one using our formula again. So let's identify the variables first. And so let's do that. So we get P, Q, N, and R. I like to define the variables, actually write them down. You might get partial credit on a test if you do this, so that'd be the way to go. Was probably not getting a 4. So this time success is not getting a 4. So P is 5/6 according to the way the question is worded. Q is failure, which would be 1/6 of the time. Those have to add up to 1 every time. Failure, success add up to 100% or 1. And there are still 3 trials. And we want to not get a 4. So I want 0 successes. It's kind of weird, but I want to get successes, not getting 4. I want that to happen 0 times. In other words, I want to get 4s. But let's just kind of figure this out. So this will be NCR, so it'd be 3 choose 0 times P, which is 5/6, to the, let's just double check this, to the R, which is 0, times Q, which is 1/6, to the N minus R. So get your calculator out. And we're going to type this in. So this would be NCR 3 comma 0 times 5/6 to the 0 power, which of course is just 1, times 1/6 to the third power, or 3 minus 0 power, which is third power. We get 1 over 216. 1 over 216 is our answer. By the way, because this was essentially saying you want to get a 4 every time, I could have calculated this easier. Getting a 4 is 1 out of 6. I'm getting the same answer every 3 times. So in this case, it's kind of an easier problem. I could have actually done 1/6 times 1/6 times 1/6. Oftentimes with probabilities, there's different ways to get there, and you'll get the same answer, 1 over 216. According to studies, it's been claimed that 65% of all single men in Montreal would welcome a woman taking the initiative and asking for a date. You challenge a study by forming a little experiment. You randomly select 15 men and ask them if they would be comfortable. If the claim made by the study true, what is probably that? Okay, exactly 9 men would say yes. So the key on this is I want you to, use the binomial theorem and figure out what P is, what Q is, what N is, and what R is. So let's just identify those. If you can do that, then it's just really plugging into a formula at that point. So I want to get 9 people to say yes. So success in this case is saying yes. What's the probability of saying yes? It says 65% of all single men would say yes. All right, they're all for a woman asking them out. So 0.65. Q is failure, so that's got to add up to 100%, so that would be 35% or 0.35. And how many people were asked? There were 15 trials. And I want to get exactly 9, so I want to get 9. So now it matter of just plugging into the formula, right? This would be NCR, so 15, choose 9 times P, which is 0.65, to the R, I believe, which is 9, times Q, to the 0.35, to the N minus R, which is 15 minus 9. And you just type that in your calculator and get your answer, whatever that is. Exactly 6 men would say no. Okay, so let's figure out what this is. So this is P, Q, N, and R. So P is, I want to say no. So no is 0.35, because that's success. 0.65 is failure. N is still 15. And this time I only want 6 successes. So if I plugged in this formula, this would be 15, choose 6, times, I guess, P 0.35 to the 6th, and times 0.65 to the 9th. This is the 6th there. And what's interesting about this one, I don't know if you see it, these two are actually the same. These two are actually the same. And I think these are the same. Let me double check that. Let's just kind of think that through. NCR 15, 9, NCR 15, 6. Yep, they are the same. So we get whatever the answer is, I haven't typed it all in. We get the same exact answer. Does that make sense in this problem, that these answers are the same? Well, if 9 men said yes, that would mean if there's 15 men, 6 men would say yes. No, so actually this is the same question in disguise. Wow, that's really interesting. More than 12 men would say yes. Ooh, now we're getting tricky. So more than 12, that would mean I'd be happy with 13. That would be success. 14 men saying yes, or 15 yeses. We're looking for lots and lots of guys to say yes to this. So more than 12 means 13, 14, or 15. So in this case, I've got to actually, it's going to be, P, yes is, so P is 0.65, I believe. That's saying yes. Q is 0.35. And of course, it's still 15. But R really is 3 different answers. It's going to be 13, then we've got to figure out 14, and then we've got to figure out 15. And we're going to have to add these 3 totals together. I'm not going to work that out. but that's what you would have to do in this problem to answer it.